Hello ladies and gentlemen, and welcome to today's training titled How to Use Real-Time IoT with Integrated Machine Learning to Solve Business Issues. My name is Mario and we'll be in the meeting for the first 15 minutes. I'm logged into this meeting as meeting operator. If you have any issues, you can contact me by typing a message in the chat window. You can contact us, also send us an email to breaksap@microsoft.com. During these sessions, you have the ability to ask questions using the IM window. Please note that the session is being recorded. And now I would like to welcome your instructor. Aditya Vasak, you have the floor.
Thanks. Hi everyone, welcome to today's webinar that was titled as How to Use Real-Time IoT with Integrated Machine Learning to Solve Business Issues. My name is Anindita and I'm a Partner Technical Consultant in Microsoft Global Partner Services team. Today in this webinar, it would be more or less towards advanced level discussion on using Azure Internet of Things and the machine learning approach. It would be basically a demo-centric session that will be covering a lot of technical in-depth demonstrations on industrial IoT sectors. We'll be talking about connected factory scenarios, connected vehicles, and also we will be checking up a lot of information and analytics over predictive maintenance, predictive analytics, and how to use that in real-world business problem. So with that, I have also shared a quick poll to understand your level of experience currently with Azure IoT and machine learning. So feel free to share your experience in the poll. That would be really helpful for me to understand. And also today I am accompanied with one of my colleagues, Pratik is here as well. So feel free to write any question if you have in the chat window. And Pratik would definitely reach out to you for any technical issues and anything related to technical content related queries. So definitely I would answer, or in case anything has been missed up, so Pratik will be there to help. All right, so please fill the poll and we'll be starting in the next few minutes. Thanks. All right, so let's get started with the webinar. So thanks to all, first of all, for sharing your quick insights regarding the first poll question. And let us get started with the webinar, how to use real-time IoT with integrated machine learning in order to solve a real-world business problem. So as we are discussing that today, our agenda is based on a quick overview on today's IoT market, what is all about IoT, when we have started to choose about Internet of Things, Internet of Everythings, IIoT, IoE, and what is the difference between M2M with IoT. And then we will be moving towards discussion about why to choose with Microsoft IoT, what are the factors, what are the different types of IoT scenario we face in real world problem, especially in the business use cases, and what are the benefits that we have in terms of Azure related IoT offering, the cloud-based IoT offering. And we would be also having a lot of demos in terms of connected scenarios like connected vehicles, connected factory, industrial revolution, that Industry 4.0, We'll be also checking up the various Azure technologies related to Internet of Things like Azure Machine Learning, Azure Stream Analytics, Azure Event Hub, and also we'd have a detailed discussion on Azure IoT Hub as well. And further, we would dive into some more demo discussion on predictive analytics, and would also have at the end end-to-end architecture discussion and the demonstration on a customer case study with IoT related to predictive maintenance. So I hope that looks good to you. So let's get started. So as we all know that in terms of understanding the IoT scenario, even 5 years back or even just like 10 years back, the scenario related to IoT was that a few questions was that what was IoT, when did it start, how did it start, and all about that. And what is the difference between M2M, that's machine to machine, IoT, IoE, and what are the different names. So if we try to understand the fundamentals of IoT, that is the machines or devices connected to each other in the network. So typically, which is not something really new and radically changing. So today we know that IoT is a buzzword to everywhere, and there is about like how we can make the machines to be more intelligent, more smarter, and talking to each other just started long before most of us even thought about it. So back then it was called as a machine-to-machine data communication. Now, in the early 1950s, there was a lot of machinery that has been deployed for aerospace and the military operations required for automation, communications, and remote access for services and maintenance. So, in those scenarios, telemetry was there, where it all started. So, it is a process in which a highly automated communication was established from which the data can be collected by making the measurements at remote or inaccessible geographical areas that could be sent over the receiver through maybe a cellular or the wired network connection, where it was monitored for further action. So to understand that better, even we have seen that the satellite communication, that a huge number of sensors have been installed in a space shuttle to monitor the physical conditions of astronauts. So those environments are also the condition of the space shuttle. The data that has been collected through this sensor has been sent back to the substation located on Earth, where a team that would use this data to analyze and take the further decisions. So some of these industries where failures could be catastrophic also saw the rise of machine-to-machine communication and the remote monitoring feature. So it was started all with the machine-to-machine communication, or M2M, that was born and mainly through telemetry. But unfortunately, machine-to-machine communication didn't have the possibility of scaling to a particular extent that it was supposed to be, and that was largely because of the time that when it was developed. So back then, cellular connectivity was not widespread that time, and it was not that much affordable, and installing sensors and developing the infrastructure that's to gather the data from them was very expensive deal. Therefore, only a small chunk of business and military use cases could be able to leverage that time. As the time passes, the internet was born and flourished exponentially. So over the last 7 years back, the number of devices that could be get connected and the internet was colossal. So computing power, storage capabilities, and the communication and technology infrastructure, these have scaled massively. Additionally, there was need to connect the devices to the other devices being involved. And the cost of setting up the infrastructure for this, it has also become affordable and agile. Thus came the Internet of Things. So if we say today the difference between M2M and IoT, that was initially was that the IoT has been used for the internet, that's IPv4, IPv6 as the medium, where the M2M could be used as cellular or wired connection for communication, but this was mainly because of the time that they evolved in. Today, the heavy engineering industries, they have used machinery being deployed, the communication over IPv4, IPv6, it is barely over the network, and it's called industrial IoT, and sometimes we call it as M2M. The difference between the two is that the bare minimum, and there are enough cases where both are used interchangeably. Therefore, we can say that even though machine-to-machine was actually the ancestor of IoT, today both are pretty much the same. Like machine-to-machine or IIoT, that is Internet of Everything. That's today, nowadays, it is being aggressively used in the market for IoT disruptions in the industrial sector. So Internet of Everything or Internet of Things was a term that was surfaced on the media and internet very recently. So the term first was coined by Cisco with a very initiative definition which emphasizes the humans as one dimension in the ecosystem, and it is a more organized way for defining the IoT. Now IIoE, that is Internet of Everything, it has logically broken down the IoT ecosystem into the smaller components. So today, whenever we are talking about IoT, the network connections of people, data, process, and things that we have been referring to. So that's why the landscape has been changed a lot over the last 7 years. From 2010 to 2017, you could be able to see that not only just a few machineries that has been involved together to being connected by the network, it has been connected from your home to workplace to again back to home. So if you see about the logical stack of IoT in the sense like Internet of Everything, so it is consists of people, process, things, and the data. So people, that could be like how we are, that we interact with devices and other people on the daily basis. So with the advance of IoT, we have sensoring, like we have different types of sensors capturing the informations and characteristics at more granular levels than ever before. And we can also accurately define the people as a complete dimension, like a personalized experience that would be a complete game changer. The smartwatch industry is also investing the homogeneous effort to get the offering more personalized. Similarly, we have processed. So in IoT space, we have the scenarios of process, like process dimension in the IoT that comprises of the software, protocol, and infrastructure. Software is mainly consists of the operating systems that's in the devices that IoT requires a special kind of operating system or operating devices. So smart devices such as like smart refrigerator, smart microwave, and many others that require an operating system that's running on them, and then it can be enable enough to be as like active component in the network. So tasks executed on them, they can vary from sending, processing, and receiving data, or executing the instructions, or sending the signals to the respective controller. So one of them, Google recently announced an operating system for IoT is called Brillo, which is an Android-based operating system. And similarly, there are a lot of advanced softwares have been there in the market. If I talk about protocols, so for IoT communication, there is a need for having the protocol because devices which are software enabled, we need to get a protocol in place that can help them to communicate with heterogeneous services to be connected to. So basically, IoT protocols is a communication platform for IoT devices that enables devices setup, phone to device to cloud communication, the user interactions from mobile devices to the web, and it has used productivity in the developers' efforts by easing up the device interoperability, regardless of the brand of manufacturer. Similarly, if you say for infrastructure, so infrastructure can simply be defined as an integration of operating system, communication protocol, and all. So all the major cloud infrastructure providers that's being focused with Azure IoT, if I say, for example, from Microsoft. So all these types of IoT solution, it integrates with the disparate systems to work together to make the ecosystem become more scalable, agile. And finally comes to the business processes and the things and the data. So things comes from the crux of the IoT ecosystem. They include like any forms of sensors, actuators, or other types of devices that could be like integrated into machines or devices to help them connected to internet and communicate with other devices and machines. For example, today in your home, that could be like refrigerator, TV, microwave, that would be considered as a typical use cases. So sensors installed in those devices, they capture the data and send the information or signals to the other devices that can be then used to take the necessary actions. Data. Data by all means, it's the most valuable assets in the dimension of IoT ecosystem. So today, the devices that are connected to the internet, they are capable for capturing the tons and tons of data that can represent the most granular level details for the devices that are connected to. The magnitude of the data, it is colossal. Storing and processing such vast and the varied amounts of data questions the fact that whether the data is really valuable. So in the true sense, most of the data is transient in nature and it loses its value within the minutes of generation. So typically, If I take an example, like with an ever-improving technology and computing capability, the amount of data that's to be processing and storage, or that depends on the devices and it capable of today, it's the great. So tons of algorithms can be executed, and the business rules can be also applied, where a lot of value can be extracted from the data before sending it over the server. And it requires a lot of combinations of multiple disciplines that's together to solve the problem and to business value. So all over, in IoT is all over just in the problem life cycle. It's more about like people, process, data, and things. That's all together. It comprises of an Internet of Things infrastructure. So with the smart progress of IoT in every dimension in the industry, you could be able to see these associated problems are also diversified to the respective domains. So they have been classified in the different names such as consumer IoT, industrial IoT, healthcare IoT, and so on. So consumer IoT, basically which types of scenario we could be able to see in Internet of Things in terms of connected assets and connected operations, like healthcare, home automations, electronics, to industrial IoT like in sectors of energy, oil and gas, manufacturing sectors. Environmental IoT refers to especially IoT use cases related to agricultural, environmental monitoring sectors. And especially the infrastructure IoT, it refers to the smart cities, smart buildings, and connected operations. So today, IoT is a concept that typically related to the features that how we can define, we can schedule, basically we can predict the nature of unscheduled downtime, or we can typically predict there would be a production failure. We can suspect a production failure, and in based of that we can take the necessary actions. So that's the line where IoT can be helpful for our business scenarios, where we can predict the nature of the failures, we can predict the timing of those such failures, the devices issues, and based on that we can take the necessary actions that needs to be taken care. So today, if you say for Internet of Things related to predictive maintenance scenario, so you could be see like how industries today are using Internet of Things in terms of IoT for manufacturing, IoT for smart cities, IoT for transformation, and IoT for transportation, retail, healthcare, like that. So with that, one of the major scenario that we know, and we are going to focus more into today's webinar, it is based on preventive maintenance scenario. So preventive maintenance scenarios, again, it is just a simple use case that you have been able to see that as a company executive, for example, like Carl, who owns a company that operates on vending machines. So his job is to just to make sure that the vending machines are selling the snacks and drinks, and the machines having working properly on time to generate a good revenue. Now, Carl wants that revenue to be always high and business has to be profitable. Now, what are the necessary steps that he can do? So in terms of preventive maintenance scenario, sometimes the machines are not being working properly, it got failed, or it may take time to fix. Sometimes some machines have been got down in the production line. So obviously it hits the sales. So in order to optimize the revenue, Carl needs a way that to identify the failed machines later faster, and even just better fix of the machines before they fail. So in order to predict the unscheduled downtime in the production line, Carl has to make a business decision for which he could be led into Internet of Things solution. So here, if I talk about a little bit about such kind of scenarios over there, like how to optimize the issues related to your devices, apply the usage tracking, apply the machines grids to deliver a reliable, efficient, and the greener transmission system while lowering the rates of production failure. And the scenarios where vending machines, but not limited to them. This is just a simple story that I was being mentioning about. It could be not just related to even manufacturing sectors. It could be related to smart city. It could be related to oil and gas, to HVAC devices, to security devices, to fire detection services, or even home automation or healthcare sectors as well. So today, with that, I'm going to show you a very quick demo on how the real-time streaming and especially with Azure IoT can work together. So as I was talking about, Azure IoT, it's all about just transform your operations into the business values, which typically has been useful to optimize the energy usage, the create the safer cities, safer operations, and to create the smart buildings, improve the field services like that. So there are a couple of use cases being available with Azure Microsoft IoT solutions with smart cities like smart buildings, connected field services, remote monitoring, predictive maintenance like that. So in the current architecture right now, as you can see, it is all about like how a real-time end-to-end streaming architecture has been built to. So technically, if you see, there are several steps related to making the millions of billions of data which has been generated from the multiple thousands of sensors to make those data into the actionable insights. To unlock the deep insights from data, we need to build technically an end-to-end architecture pipeline. That's we refer as real-time streaming architecture. So in this building of real-time streaming architecture, we need to have some steps of definitions like from event producers to collection of those data, to ingestions like ingester or the brokers, to transformations, and finally the visualization or the presentation. So if I talk about like as the demonstration, like the predictive maintenance scenario. So predictive maintenance, it's all about like anticipation of your maintenance that needs to prevent the equipment failures and to avoid the unscheduled downtime. It is all about just analyzing the streaming data to quickly assess the conditions, recognize the warning signs, and preemptively service equipment before costly repairs are needed. So there are actually the steps, while in terms of designing and implementation of those kind of scenarios, in spite of potentials of the predictive maintenances of IoT. So typically, if I say in terms of streaming architecture, we have to understand, first of all, the event sources, like the devices or the sources of events which has been capable of generating the data. So it could be like various sorts of applications in predictive maintenance scenario, or it could be the various types of LOB apps or the legacy IoT devices. It could be IP capable devices like Windows or Linux, or it could be even the low power devices like RTOS capable operating system devices. So with that, once the devices, this Internet of Things, like those types of IoT devices, is being capable enough to generate the data, the next step is obviously going to be how we could be able to capture the data. So once to design the business opportunity, like identifying the inventory data sources, then comes to gain the predictive insights, like how to capture and combine the data. This data capturing that could be possible through the various sorts of gateways. So in implementation side, we normally use various types of cloud-based web APIs, REST API, or various IoT gateways or field gateways that's to be connected directly through event hubs, Azure Service Bus Event Hub. Azure Service Bus Event Hub overall, it's a resource that's being capable to process the complex events over the period of time, and it is also possible that through Event Hub, which is a highly scalable data streaming platform and an event ingestion service, which is capable of receiving and processing the millions of events per second. So here, this types of real-time streaming architectures, event hubs could be used to process and store this millions and billions of events coming from the various devices, data, telemetry that is being produced from those devices by distributed software and the devices. So data sent to an event hub, it can be transformed and stored using any real-time analytics provider or by batching or storage adapters. So Event Hub has the capability to provide the publish subscribe capabilities with low latency and massive scale. So Event Hub servers as an on-ramp for big data. So from the Event Hub, once the data has been captured and processed through, further we could feed the Event Hub data into a managed, cost-effective, real-time event processing engine, which is based in Azure, which is known as Azure Stream Analytics. So Azure Stream Analytics is a resource that is being capable to make it easy to set up a real-time streaming analytic computation structure on data streaming platform from devices, sensors, websites, social media, applications, infrastructure systems, and many more. So today in Azure portal, just a few clicks, we can author a stream analytics jobs and we can specify the input source of the data ingesters, that is as an event hub or even IoT hub, and even we can specify the output sink for the results of your job. And the data transformation in the stream analytics, it's expressed in a SQL-like language, which we can monitor and adjust at the scale or speed of the job in the Azure portal in order to scale them from few kilobytes to a gigabytes or even more of events processed per second. Stream Analytics, it leverages the years of Microsoft research work that is to be developing in a highly tuned streaming engines for time-sensitive processing. Also, Stream Analytics has the capability of language integrations for initiative specifications as such. So, we have been passed in the webinar, we will be exploring more insights about Stream Analytics. Before that, I would like to talk about, in brief, about few of the capabilities and benefits of Stream Analytics. Stream Analytics overall, it's the easy-to-use resource which could be capable to process the complex event processing architecture model. It has a feature to support a simple declarative query model for describing the transformation in order to optimize for the usage. So Stream Analytics typically uses a T-SQL-like variant, and it removes the need of customer to deal with complex technical details in terms of stream processing system or to design the complex query patterns. It has the capability like to define the common operations like in T-SQL-like language interface like joins, aggregation, projections. And also with Stream Analytics today, we can implement the time series queries, temporal-based joins, windowing functions like that, which I'll be showing in the demos. Stream Analytics is a very well capable of handling the high event throughput, even up to 1 GB per second. So it has well-known integrations with Azure Event Hub, IoT Hub, which allows a solution to ingest even millions of events per second, which is coming from those connected devices, maybe click streams or the log files. But in order to achieve those end-to-end processing systems, Stream Analytics leverages the partitioning capability of Event Hub, which can yield up to 1 MB per second partitioning strategy, like data could be stored in the various partitions. So where users are able to partition the computation to a number of logical steps within the query definitions, and just each with the ability to be the further partition to increase the scalability. Apart from that, Stream Analytics is as a cloud service system managed solution. So it is optimized to provide the user a very low cost get going and maintain the real-time analytics, which maybe needs to optimize the real-time data processing architecture if going to use the optional one or even the comparative one technology that we have through using the Hadoop services in big data architecture, using the Apache Storm for real-time processing. But that needs a good level of dev times, like to have a good development skills into the various languages like either Java or the REST or even few .NET C# APIs that we have been helped for. And we have to be also being capable to design a good level of architectural decisions in terms of Hadoop cluster setup, monitoring and administrations. While the same comparative technology in Stream Analytics that's providing the same facilities of real-time event processing, it has the ease of usage, it has the capability of reliability, repeatability and quick recovery process because it's a pure managed services in the cloud. So Stream Analytics helps to prevent your data loss and it provides the business continuity in the event of failures through our built-in recovery capabilities. So with the ability to internally maintain the state, the service provides the repeatable results, ensuring that it's possible to achieve the events and reapply the processing in the future, always getting the same results. And this enables customers also to get back in time and investigate the computations while doing the root cause analysis, what if analysis like that. And overall, Stream Analysis has also the features of user-defined functions. Any point of time, you can call any UDF functions from like JavaScript, or you can use an end-to-end connectivity model with the real-time data ingesters like Event Hub, IoT Hub with Stream Analytics, or even you can put the output sources like Azure Blob Storage, Azure SQL Database, Data Warehouse, or service bus topics, queues, or even if you would like to have an end-to-end near real-time visualization through Azure Power BI. So before jumping into the demo for today, I would like to talk in brief about the Big Data Lambda architecture. So Big Data Lambda architecture, as we all know, it comprises of 3 layers basically. That's we have like batch layer, speed layer, and serving layer. So in terms of Big Data Lambda architecture model, we have the facilities that to have 2 layers, just that we refer as the hot path and the cold path of data. So hot path that refers to as like the data at rest. So that we can define as like that once the data has been at rest, that we refer as a cold path. So while the data has to be stored, it has been coming from the various batch processing layer. Data may be having stored for a couple of weeks or for a month or even for a year. And the data from those business apps or the LOB apps that needs to be stored in a batch processing mode, like through a Hadoop cluster. And from the Hadoop cluster, on top of the data lake architectures, we can process the data further, apply more intelligence on top of data using Azure Machine Learning. And from the Azure Machine Learning, we can further process, we can take a near real-time visualization through Power BI. So that was about the cold path or the data at rest motion layer architecture through the Lambda architecture model. Similarly, we have, if you say from the top layer of the architecture pipeline, you can see that the data in motion layer. So data in motion layer, which has to be defined as a hot path. So which is basically refers to as typically the speed layer. So in order to define the cold path, that's where the hot path, that's the speed layer, which defines like how fast the data could be processed into and how fast we can get the insights from the data. So here the data which is being generating from the various types of devices, sensors, or different types of web models. So from the diagnostic streaming, the data at the speed, it could be processed, ingested after ingestion from the event hub. It could be processed into Azure Stream Analytics. And from the Stream Analytics, it could be further processed on top of that by applying the intelligence and the various types of machine learning algorithms like clustering, classification, regression. And after that, it could be again passed into from Stream Analytics machine learning layer. It has been pushed into the near real-time visualizations like through Power BI. So overall, if I talk about the speed layer facilities, that about the functionality of the speed layer, so we could be able to define that apart from the batch layer and the serving layer, speed layer, it's all of the facilities like as a similar to the batch layer, but it has a capability that it produces the views based on the data that it receives from. So there are some key differences, of course, in Lambda architecture, like the speed layer, serving layer, and the batch layer. So one of the major differences is that in order to achieve the fastest latencies as possible, the speed layer doesn't look at the new data at once. Instead of that, it updates the real-time view as it receives the new data instead of recomputing them like the batch layer does. So that's why speed layer sometimes is called as incremental updates as opposed to the recomputation updates. Another biggest difference is that in terms of hot path or cool path analysis, like data at rest or data in motion. So you can define like was the batch layer, the speed layer also maintains a view from a key. Like it could be key based on the URL or the hour to a page view count. And also unlike the batch layer, speed layer also recomputes the mapping from scratch each time. So the speed layer, it modifies its view as soon as it receives the new data. Also, the speed layer, it also requires the databases, just like as the hot path I was talking about, which you can see at the top layer of this architectural layer, from data sources, ingestion, prepare, and analysis phases to further publishing and consuming phases. The speed layer requires the database that supports the random reads and random writes, because these databases support the random writes, and they are orders of magnitude for more complex than the databases that you use in the serving layer, both in terms of implementations and operations. Now, if you see the importance of Lambda architecture, the beauty of this Lambda architecture is that once the data makes it through the batch layer and then into serving layer, the corresponding results in the real-time views. That means you can discard the pieces which are no longer needed real-time view as they are no longer needed. So this is a wonderful result. It's an awesome view. Since the speed layer is a way that's to have more complex than the batch and the serving layer. This property of Lambda architecture is called as complexity isolation, meaning that the complexity is pushed into a layer whose results are only temporary. And if anything goes ever wrong, you can discard the state of the entire speed layer and everything will back to be the normal within a few hours. And this property greatly limits the potential negative impacts of the complexity of the speed layer. And finally, even the speed layer and serving layer, which is actually a mixture of batch and the speed layer data architectural platform, the last piece of the Lambda architecture is the merging results from the batch and the real-time views to quickly compute the query functions. So once you have defined the merge layer architecture, so basically that you must be defined about the queries that from the speed layer and the serving layer, which could be merged into a complex data functions, or which could be merged again from the recomputing functions. So speed layer compensates for the high latency of updates for the serving layers. It uses for the first incremental algorithms and read-write databases to produce the real-time views that are always up to date. Speed layer also only deals with the recent data, whereas batch layer deals with the data from the gathered from the weeks, over the months, and over the years. Whereas speed layer, it is being capable of for working on the very recent data that just comes, it processed it and produces the results. So because of any data which is being older than it has been absorbed into the batch layer and it has been accounted for in the serving layer, speed layer is significantly more complex than the batch layer and the serving layer. But the complexity is always compensated by the fact that the real-time views can be continuously discarded as the data makes way through the batch and the serving layer. So the potential negative impact of the complexity through speed layer is greatly limited. So next we are going to check a quick demo on vehicle telemetry analysis that's being called as the demo on connected car. So before starting with the demo, I would like to define about the architecture of connected car scenario. So basically, this particular architectures and the demo, it is being based on the hot path as well as the cold path of analysis. So since we have been talking today, let me switch back. Okay, so since we have been talking today mainly through the connected car scenario, and we have been talking mainly to the hot path of analysis for today in terms of Internet of Things scenarios. So we'll be defining overall that how the end-to-end architecture has been built into. So we have like from the various steps of implementation designs, like from data sources to ingestion to preparation to analysis to publish and finally to consume. So if you say first of all there are two layers, like as usual hot path and the cold path of analysis. So first of all, in the cold path of analysis, we have from the data ingestions after it has been happened, data coming from various sensors or apps, it has been stored, it has been ingested by the various partitions of Event Hub, and from the Event Hub it has been pushed into Stream Analytics and further pushed into Azure Blob Storage. Now here comes the differences, like after first level of processing, what would be the appropriate data architecture could be. Either it could be going to be the hot path of analysis or it could be going to the cold path of analysis. It again depends on your analytical scenario, your analytics question that you want to identify from the production line item scenario, that what type of analytics you want to go for. So normally in terms of vehicle telemetry analysis, we do a cool tier path, and also we define a hot tier path. Cool tier path, that where the data basically comes from the batch processing layer, that again from the blob storage the data has been stored on top of through the compute layer, that is we can compute the data in batch processing mode through some Hadoop clusters, like using the queries from pig and hive scripts, and on top of that we can even further process it through Storm, Apache Storm tuples, and effectively we can derive some anomalies on top of through the Hadoop clusters, and we can define some sorts of again some intelligent algorithms, like we can define the machine learning libraries and machine learning algorithms on top of the processing data. And finally, those historical data from Hadoop clusters we can further push into in the databases for long-term storage, maybe in the Azure SQL Data Warehouse, or maybe we can further from there we can push into near real-time visualization, or just quite real-time visualizations like through the Power BI dashboard. that is all about like data at rest or the cool path or the cold path of architecture layer. But if I say in the solution architecture on the top level, that how the data analytics could be going on, if you want to have just in real time or absolute real time architecture, if you want to build up such kind of absolute real time or just in real time pipeline model, you have to process the data from stream analytics to directly, you can apply on top of that through further analysis some kind of intelligent machine learning algorithms like classification, regression, anomaly detection, such kind of ML models which you can today directly integrate with stream analytics layer. And finally, we can push it to further into Event Hub, or we can directly push into Power BI for just absolute real-time dashboards. So with that, what I'm going to do, I am going to present my desktop here so that I can share with you the end-to-end pipeline model. So what I have is basically, for this demo, I have basically both the layer to be present with me. I have the hot path as well as the cold path of the vehicle telemetry analysis. So first, I'm going to show you the absolute hot path, that the path which is coming from the device's car event sensors to process through Event Hub to Stream Analytics, next directly through Power BI with Azure Machine Learning Intelligent Layer. And also I have a cold path layer architecture as well for connected car scenario, where the data has to be coming from the first level of streaming analytics model to, again, it has been pushing into some Hadoop clusters through some HD Insight Storm cluster. It has been processed the events in absolute just in real time or just in near real time, but it's mainly used for the batch processing layer through using some Storm tuples and bolts. And furthermore, on top of that, we have stored the data into Azure SQL database for long-term permanent storage. And from there, we have also built a near real-time visualization, quite near real-time visualization. So to define this architecture, let me show you first the event generator. So I have just switched into my dev machine here, and let me stop a bit to show you the data generator. So here you can see that in the Visual Studio, I have the applications for the car event generator. This application is responsible for generating the millions of events from the various cars. The story line is basically, the demonstration is based on the 4 cities over the city of Seattle, Bellevue, Sammamish, and Redmond. And what are the number of cars that has been passing on each and every day for those 4 cities, how many events has been generated from those cars, the pollution index from those cars, the vehicle status. Basically, almost we all are being sensible about the car health status or the equipment's health status whenever there is any failures happened, like the oxygen duct is not working or something being wrong with the car tires or through the engine systems. But how we can detect, how we can predict such kind of equipment failures in real time, and we can take the actionable insights, we can take the appropriate scheduled actions before such failures happen to those devices. So that is almost about the objective for doing the connected car analysis or the vehicle telemetry analysis. So here we have been generating in the virtualized environment, the data related to like different car equipment status, like the high speed probability power, low oil probability power. You can see also the outside temperatures, the temperature status indexes. And basically, as I said, that this particular demonstration has been initially performed over the 4 cities in the city of Redmond, Seattle. And also we have used not only just absolute real-time data that has been processed through Event Hub, but also we have some kind of static data references as well, which we have stored as a CSV file into Azure Blob Storage. So in this demo, you can see the master list, which consists of the vehicle ID indexes, the vehicle car indexes, and also we have the, according to the vehicle ID, we have the vehicle model, so that we can define a vehicle-wise analysis further in the different cities, their equipment status, the equipment, probable equipment failures. So those kind of details we could be able to get. So once I run this particular application, so this application would be responsible to generate just in real time this thousands and millions of events per second. And this particular events have been processed through in a stream analytics and the machine and also in an Event Hub job. So in the Azure portal, as you can see, I have opened the Azure portal at this moment. So in the Azure portal, you can see I have already created a stream analytics job called vehicle telemetry. Now, if I move further into the job, in the stream analytics job, you could be able to see that I have already configured the inputs, the query that I have implemented, and the outputs here. So I've not started the job at this moment. So just to show you the end-to-end the architecture details about the stream analytics jobs, and then I will be starting the job once again. So in the input sections of stream analytics jobs, once you provision today in the Azure portal, so in the Azure portal today, you can provision a stream analytics job just from starting from new, and you need to select from new in the marketplace. You need to select under Internet of Things, and you can provision the Event Hub, you can provision the Stream Analytics job, and even all the related resources related to Azure Internet of Things, you could be able to get under Internet of Things pane. So if you are working for the event ingesters like Event Hub, you can select Event Hub, and you can start provisioning an Event Hub job from there. Or if you are planning to use IoT Hub, you can use the IoT Hub, you can provision the IoT Hub. IoT Hub, again, it's a managed connected services for IoT devices. And also, you can use Stream Analytics job. You can provision a Stream Analytics job just by provisioning directly from portal itself. So, okay, so there is a question for Janavi. Would this recording be shared with us later? Yes, Janavi. So we will be sharing this recording to all of our attendees today within one business day itself. So you can provision a stream analytics job. So once you select from under the Internet of Things pane from the new sections of Azure portal, so what you have to do first, you need to provide the name of the stream analytics job. Then you need to choose the appropriate subscription. After that, you need to choose the appropriate resource group, because today almost all the resources in Azure Data Services and in Internet of Things, or even in Azure PaaS services, that comes under a resource group. So resource group, it's an ARM template. It's the collections of resources that share the same lifecycle, permissions, and container level policies. And finally, you need to choose the location. So here there is a vast amount of locations are available for stream analytics job. So you can choose your appropriate nearest location. So for this demonstration, I'm choosing my nearest location as the Southeast Asia. And once I choose the location, we can pin into the dashboard, and finally we can click on create, so that we could be able to identify the level of provisioning time in the Azure portal itself. So for these demonstrations, I already provisioned for vehicle telemetry analysis. So I'm directly jumping back to my stream analytics job. All right. So as you can see that in my vehicle telemetry analysis stream analytics job, so I have already provisioned the input, the query, and the output layer. So in the input layer, as I was talking about, I have defined two specific input layer. One is the event hub that is being capable for ingestions of the real-time event. That is, once the events have been coming from the virtualized C# simulator, that's it generating the car events over the seconds. So once the events has been connecting, it has been directly ingested into the event hub. So here, this particular event hub, which is loading right now, it is being in this particular event hub, the events has been ingested to just in real time. So this is the particular event hub in the service bus namespace I have already configured as a vehicle telemetry. I have also provided the event hub policy key, event hub serialization format like either JSON, or if you are working any point of time, any serialization formats like Avro or CSV, or any specific encoding other than UTF-8. So you must be providing the details about the event hub in order to register the event hub with stream analytics. And also for this demo, I have added a reference stream as a reference source type, that is the blob storage. So in the blob storage specifically, the CSV files that I have demonstrated in the Visual Studio C# simulator, especially the vehicle index number CSV file and the vehicle model with the index numbers, those particular CSV file which has been stored there. So those particular static data files which I have stored in the blob storage, I have added also as a reference stream in the stream analytics pipeline, input pipeline. Now, once the input has been built up, the next part that I have to do is to define the query. So in this particular stream analytics job, I have defined this query. So let me increase the font a bit. So here, I hope you're able to see it properly. So here, just being, so this is my stream analytics query that I have used for vehicle telemetry analysis for the hot path scenario. So here basically this is the query that I have used. So you can see that how easy to write the T-SQL query like interface for stream analytics. So we have used the input data path, that is from the event hub and the blob storage path, and we have also defined the various schemas for event hub data that has been ingested to the vehicle engine oil indexes, tire pressure, odometer, city, accelerator pedal position, the headlamp status, the brake pedal status, such kind of details we have provided. And also after we have defined the schemas, we have also defined the output path, that once the data has been processed to, what could be the output sync layer. So either it going to be the Power BI, because for the hot path tier I have directly ingested the output into the Power BI, but you can also from there in the output you can choose Azure Blob Storage for long-term storing purposes. You can put into the RDBMS database as well, like you can choose Azure SQL DB as an output, or you can choose Azure SQL Data Warehouse as well. Or even you can further ingestions and further processing and partitioning. You can choose Azure Service Bus Event Hub as well, or you can choose Azure Table Storage or Service Bus Queues or topics. So such kind of, or even Document DB as a NoSQL database storage. So such kind of offerings we have today. And further also I have applied here a joining facilities from the ASS SQL features. So ASS SQL, like Stream Analytics SQL, has some features today, like we can apply the joining, like SQL joining operations. Here is a simple join being happened. Apart from that, we can even apply the windowing functions. So there are three kind of windowing functions is available, like in terms of defining the windowing intervals, like how fast the events could be processed to, and to define in terms of data overlapping or non-overlapping nature. So we have like sliding window, hopping window, such kind of windowing interval is also available. All right. So next to show you the output layer. So here we have, as I said, like in this demo, I have directly produced the output to the Power BI. So while you are designing such kind of solutions like integrations with Azure Stream Analytics, and you want to directly integrate the near real-time visualization directly into Power BI, make sure that you have been directly, you have been logged in through your Azure account with the same Office 365 Azure AD account that you have also through the same account you have the Office 365, the Power BI account as well. So it is actually just to make sure that that's your Azure account and your Power BI account has been connected end-to-end through the same account details. Otherwise, it would be difficult to integrate Power BI settings, Power BI Workspace to import through Azure account. So here what I did, I have just imported my Power BI settings, my workspace, my database, and also I have defined my Power BI table name. And for authorizations, so I have already authorized it, but any point of time, if it's needed to renew the authorizations, so we can click the renew authorization button so that it would authorize the different accounts or in order to modify the workspace, the Power BI workspace. So that's all for about the configuration sections. Now you can see that typically in Stream Analytics jobs today, we have the options for adding up the functions. So as I said, like any point of time, if you want to add any kind of functions, like today we have the capability to add in Stream Analytics the user-defined functions. Like it could be like JavaScript UDF, or it could be like Azure ML ADF, Azure ML UDF, user-defined function. So such kind of functions we can definitely could be able to add. If you have already a JavaScript UDF which you want to integrate with Stream Analytics jobs, we can do it like that. We need to define a function alias, then you need to select the type of function, and then you can define the output type. So for JavaScript type of UDF, we have the output like any array, or it could be like big int, datetime, like that. If we have to choose like Azure ML, so for Azure ML type of functions, we can choose the output type, like we need to provide first of all the subscription details, then we need to provide the Azure ML workspace details, the URL, and the workspace key. I'll be showing next in one of the weather prediction analytics demo that how to integrate Stream Analytics with machine learning. So, so we can add even the function references, UDF function references with Stream Analytics. And also in the configuration sections, we could be able to see that we have an awesome feature with stream analytics is that the scalability. Like any point of time, if you think that your data ingestion limit, the events that has been increased from maybe from thousands to even from millions, or from millions to billions. So over the period of time, we have the capability to increase and decrease the streaming units. So streaming units, it's the pool of computation resources which is being available to process the query over the period of time. And also so very easily we can add the streaming units, even for in case of increase of the events traffic, or even any point of time if you want to decrease the streaming unit, we can do that. So today almost 48 up to level of streaming units we can configure, but of course if you want to add more, so you can always contact Microsoft support to do that. And with stream analytics, we have also the facility, like you can develop not only from Azure portal today, you can develop the stream analytics job from Visual Studio itself. So there is a tool available, that's Azure Stream Analytics tools for Visual Studio. So once you click here, even from portal, you can just install the tool and you can start working from Visual Studio to work with stream analytics. Apart from that, we have also facility to use through REST API or through PowerShell to provision Azure Stream Analytics job. And further, once you want to start any stream analytics job, so you need to click on Start button. So once you click on Start button, you should have the options like whether you want to go ahead with, you want to start the job like absolute at that particular moment, like now, custom, or when last stopped. So it is always good to specify the custom mode so that it will take your current date and time based on your current locations and your particular your time zone, and based on that you can start the job processing. So here, since I stopped the job initially, so my monitoring events, it's not showing at this moment in absolute real time. There is no input events and output events has been passed through over the last 1 hour. So just right now I have started the job. So over the period of time, within next 10 to 15 minutes, I could be able to see the nature of the input events, output events, and if there is any runtime error being associated with this particular job. So with that, here goes the Power BI dashboard, which is being representing the absolute, the near real-time visualization so far. So you can see that I have defined some of the indexes in the visualizations, like the total fuel consumptions, tire pressure, engine oil consumptions, odometer, engine temperatures, total number of car models that has been specified too. This dashboard is actually absolute real-time. It is working since in UTC time zone. So it is showing last when the job worked in UTC time period. But since already I have started the job once again, so within just in few minutes, you could be able to see that the dashboard will be refreshing in just real time. And also you can see some of the visualization in the side, in the right hand side, like the speed, fuel, engine oil consumptions by outside temperature over the 4 different cities. Also I have designed here the visualizations over the fuel consumption, total fuel consumptions over the various cities. So over the Seattle, Bellevue, Redmond, Sammamish, whatever about the average fuel consumptions per day. So absolutely we can see Seattle and Bellevue having the maximum numbers of fuel consumption unit. Yes, that's as I was talking about. So till the period of time, you can right now able to see that the speed of the car analysis. So since I've just started the stream analytics pipeline, so the dashboard has been refreshed once again. So from May 23rd, I stopped the job. So from May 23rd to May 29th, so what about the speed? And in next few minutes, we could be able to see that today, whatever the average speed for different cities. So that analysis over there. So this is this particular dashboard in just in real-time dashboard. Now, one more dashboard also I could like to show you, that which has been built into using cold path. So let me open one more workspace so that I can show you. Okay. So this dashboard, which is being actually coming from the batch layer view. So batch layer view, as we all know, that that I was even talking about, that is about the cold path of analysis. Like once the data has been processed through the first level of streaming analysis job, like from event hub, stream analytics, and it has been pushed into blob storage for long-term storage purpose. And from the blob storage, again, the data has been computed in the batch layer, where it has been stored over the period of time, over the days, over the months, over the years, and it has been computed computed on top of in a batch mode, like through Hadoop cluster. So here the data has been another layer that I have built into. The data has been processed through HD Insight cluster, where it has been processed through some batch processing components like Pig and Hive scripts, and from there those particular analytical model we have consumed the output, the data events, and we have stored further into Azure SQL database. And this Power BI dashboard have been actually built from the output of those batch processing Azure SQL database data. Whether the same data, the same vehicle telemetry data has been stored and computed through the batch layer. That's from the Hadoop clusters through, again further through Azure SQL DB. So here you can see that some of the visualizations layer I have defined again, like engine oil, fuel, average speed, tire pressures, and also the fuel efficient vehicles over the period of time. I have also defined the total car availability, the fleet compositions by the various cities, also in the 4 different cities, or whatever the various types of vehicle models that's being available. So obviously compact car or coupe, hybrid, large SUV, that's are the more preferable in especially in Bellevue and Seattle. And also the fuel efficient driving pattern. So in Seattle we would be able to see the count of vehicle indexes, and the count of average index of the cars have been more, like 856 number of cars have been there. And also I have defined some of the visualization related to the aggressively driven cars by month. So over the period of time, what are the total numbers of cars which has been aggressively driven, the wreckage having happened, or over the period of time in the various cities. Like in Bellevue, there's some maximum numbers of recalled cars by cities and aggressively cars by the various cities. So that was almost defines the analytical model, that how end-to-end such kind of the vehicle density we can define, that's the cars by city over the period of time in the various 4 cities like Bellevue, Redmond, Summer Beach, and Seattle, and also how the real-time vehicle health index capabilities we can define. So as you can see in this dashboard, the average engine oil, fuel, tire pressure, odometer, and also you could be able to see the speed versus engine temperature details, and also you could be able to see in the 4 different cities the average of engine oil, fuel, and the tire pressure components analysis. You could be also able to see that the aggressively driven vehicle status indexes. So over the different cities, what are the most of the cities that where we could be able to see the massive aggressively driven cars in almost the comparison to the other 4 cities. So in Seattle is one of the fastest all of them, where we could be able to see over the period of time the over 1,320 number of aggressively driven cars being there. Whereas if you say for comparison towards the model-wise analysis for the cars over those cities like large SUV and sports cars, mostly we're being able to see in Seattle compared to just being coming down to family, saloon, or medium SUV or small SUV. So these are some of the compositions over the city-wise analysis over these 4 cities, whether Bellevue, Redmond, Seattle, or even Sammamish. And also some of the wreckage cars, recalled vehicles. So analysis-wise, also I have made a comparative visualization on top of that. So what are the recalled vehicles by models, and what are the fuel-efficient driven vehicles? So how far they have been, how much they have been fuel efficient. What are the vehicle-wise analysis for those cars, like in terms of large SUVs, convertibles, sports cars, compact cars, like that. So mostly, as we know, that large SUVs, most of the attention has been needed, because in terms of equipment failure, though they're having a large car, they needs a lot of engine oils, they need a lot of care and attentions. So compared to the small SUVs or like a small hatchback. So also here in the Bing Maps, you could be able to see that in the city-wise analysis of the recalled vehicles, so the count of vehicle indexes, so compared to Seattle, compared to in the Bellevue, Kirkland, or compared to in the Redmond, Adelaide. So that's obviously defined the details. And also I have defined the visualization in terms of fuel efficiently driven vehicles. So how many numbers of fuel efficient cars being available. So what are the most fuel efficient vehicles by model wise being seen. So hybrid cars are the most available nowadays in West Coast. So apart from the sedan, compact car, or the sports car. And also if you see for city wise analysis, that's also I have did here, like from Seattle to Bellevue to Redmond, what are the most fuel efficient driving pattern has been observed. Microsoft in those cities in the current time. So Seattle, you can see that almost the maximum numbers of fuel efficient driving pattern has been observed. More than 850 numbers of fuel efficient cars has been observed. And these are some of the fuel efficient drivers models. So in this nice donut chart, you can see that what are the various levels of hybrid, compact, sports cars analysis that I have did that like car-wise analysis over the fuel efficient car patterns. So this is how we define the vehicle telemetry analysis model, that how today a connected assets, a connected telemetry, that we can build a pipeline end-to-end with the hot path and the cold path of the data layer. So where we can have the data at motion and we can also have the data at rest, and how we can build such kind of connected architecture through Azure Data Services. So with that, I am just switch back to my presentation deck once more. Just switching back to the presentation before starting the next demo. So hope you are able to see my presentation deck. Now, any point of time, if you face any issues to see the presentation deck or the desktop even, so feel free to type in the IM window. My colleague Pratik is here, so he should be able to support. The next demo that I am going to talk today is about the connected factory. So in connected factory, again, it's one of the major part of the pre-configured solution approach for Microsoft Azure IoT services, which helps to deliver the end-to-end solution that can implement the common IoT business scenarios. The connected factory pre-configured solution, which is available today with Azure IoT Suite and Azure IoT Platform, which is just being available from last month, April 20th, it has been released. So it is a part of Industrie 4.0 revolution. So it is as just like for connecting devices, connecting assets, and monitoring in your industrial devices. So we can use the solutions of connected factory just to analyze the stream of data from the devices and to drive the operational productivity and profitability. Not just only that, but also we can predict the possible equipment failure lifetime. We can reduce the cycle time from issue identification to solution implementation. We can define the faster response to demand changes or to supply chain disruptions. We can even transform the operational data into the actionable insight. We can continuously improve even the KPIs, health status indexes, and safety compliances in terms of factories. So if you today say that the various benefits of connected factory workplace, so Microsoft already did the various successful case studies on connected factory. So one of them is based in Ohio in US, that's a KUKA Systems, and also even one of the major vendor, Coca-Cola, they have defined connected factory integrated solution with the Microsoft IoT Suite, which able to demonstrate that how it could be enabled to improve the operational efficiencies for in terms of decision makings for faster production lines, how it could be able to reduce the equipment failures, equipment downtime and supply chain disruptions, how it could be able to retain the talent, offering engaging the social and the collaborative tools just to enable them to do their best work with the current topology. And with this help of connected factory workplace, so it has been possible that to decrease about 8.5% in the time of decision with Office 365 BI capabilities, and also majorly over 20% improvement has happened in the supply chain and the partner satisfactions, along with the companies that uses these types of social platform with connected factory. So with that, I would like to demo on connected factory workplace. So let me switch back again to my desktop. So with connected factory, that's to get started with. So we have today connected factory being available as an end-to-end solution. We have been available today in Azure IoT Suite. So today, if you get started with AzureIoTSuite.com and you have been started to bring our solutions on a connected factory demonstration, so we could be able to define a solution on connected factory. So here, if you click on Create New Solution, So you could be able to find the solution is already available for Connected Factory, which is able to accelerate your journey to Industry 4.0. That's to connect, monitor, and controlling the industrial devices for insights with OPC US servers. That's to have end-to-end operational productivity and the profitability. So if you select to start with a Connected Factory Suite, so you need to provide initially some of the details like your solution name, your subscription details, and you need to select the regions. So almost in few of the regions that the solution today available in various parts of the globe, like from US it is being available in West US, East US, in Europe in both of the data centers being available. In Asia it is available in East Asia and Southeast Asia, and in APAC it is available in Japan data centers and Australia data centers. And the solution in end-to-end, the Connected Factory with Azure IoT, it is being consist of the resources like Azure Storage Account, one VM, one IoT Hub, one Key Vault, a time series insights, and also Azure Web App. So since I have already provisioned the solution, so I'm not going to provision it once more. So what I'm doing, I'm just jumping back to my solution here, which I have already provisioned. So here I have already provisioned, as you can see, a Connected Factory, that's my solution here. So I'm quickly going to launch that solution. So it will take a couple of minutes. In the meantime, let me show you what are the Azure resources that's being provisioned. So I have the resource group, and under resource group, the number of resources that has been provisioned to build the Connected Factory solution. So you can see that I have defined a Bing Maps API because that would be needed to define the locations of the various equipments and the factories across the globe. I have a VM, I have a Key Vault, Azure Key Vault for enterprise level SSL authentication. I have the network interface and NIC. I have defined an NSG. I have defined a VNet. I have a storage account, IoT Hub. I have all have been defined in app service plan, and also I have two different time series insights environments. Now let me launch the solution dashboard for Connected Factory. So I hope you are able to see my screen. So please let me know if there is any difficulty in visualizing my screen. So this is the dashboard for Azure IoT Suite Connected Factory. So you can see that once I have launched the Connected Factory solution, so here goes in the left hand side some of the factory location. So like you can see, like I have more or less into the 6 different cities of the world, the different factories that from which the this particular analytics have been made into. So it works through the basic features of the pre-configured solution. So the scenario here is that once you deploy the Connected Factory pre-configured solution, it is pre-populated with resources that enables you to step through a common industrial scenario. So in this scenario, several factories have been connected to the solution, just reporting their data values which require to compute the overall equipment efficiencies and the key performance indicators, and like how the monitoring of the factory is going on, what are the production lines status, station, equipment efficiencies, and the other KPI values. Also, it helps to analyze the telemetry data that is generated from those devices using Azure Time Series Insights, and also it helps to act on the alerts to fix the issues. A key feature for this types of scenario is that you can perform all these actions remotely, even from the solution dashboard and within just a few clicks. So in this dashboard, you can see there are a few things having there. First of all, this defines a number of factory locations on the factories. So factory list just defines the status, location, and the current production and the configuration for the solution. So when you first start to run these types of solution, there are a number of simulated devices. The production line simulation, which is composed of the 3 real OPC US server production line, which performs the simulated task and share the data. You can see also a Bing map. You can make it more interactive even just by adding the device connected to the solutions, and I have already used a Bing Maps Enterprise API, but you can also make it a more dynamic one. Also, in the right hand side of the solution, you can see the various alerts that has been displays the alerts generated when a telemetry is like of operational equipment efficiencies, or like the various KPI values, it has been exceeded the specific threshold, and also it defines the various consumptions level, energy consumptions level, error lines like that. And also in the bottom there is overall equipment efficiency features, so which shows the operational equipment efficiency values for the whole enterprise systems, or like the factory or the production line or the station that we are viewing here. So this, all the values here, it has been aggregated from the station view to the enterprise model and even enterprise level. So the operational efficiency levels, it's actually the figure, and it constitutes the elements that could be further even analyzed over here. And also we have two more visualization that indicates the key performance indicators, so that displays the number of units that could be produced and the energies that could be used by the whole enterprise over the time, or the factory or the production station that we are viewing here. So these are all the values being aggregated from a station view to the enterprise level. Now the factories panel here that you can see, so starting from the factory which is being operating, which is not normal. Let's start with from Munich, which has reported an error. So let me switch back from Seattle to Munich. So the factories panel, it actually shows here that the geographical locations for all the factories in the solution. So let me start from Munich, which reported a braking system. So Munich in Germany, it's reported here in the connected factory solution that the current production configurations has, there is some errors. So you can see there is on the production line in the Munich factory, there is in the current configurations of the brake pads, there is an error happened, and these are some of the alerts in the right hand side you can see. So the rows in the list are basically some of the hyperlinks here that shows the link details of the production lines in that particular location. So in the city of Munich, for this particular factory, there is an issues happened with energy consumption level, which goes minimum the threshold, the energy consumption is below threshold values like that. Now it is then possible also that we can even from the factory panel, we can even further drill down to execute some of the actions. So once we click on the alerts details, we can execute the alerts defining situations like on the particular time zone. So whatever being happened in the factory panel. So the factory list also initially shows here that we define the 6 different factories. Now also we could be able to define the details of the production line, and we can also even view the published OPC UA. So here, if I drill down further into the error line items, like in the error in the production line, so I could be able to see, I could be able to drill down further that in which particular equipments that particular errors have been happened. So in the Munich production line 1, there is an error happened through the test session that there was a brake pad test station and some energy consumption going below the minimum threshold value. So if I click on that, I could be able to see that some of the alerts related to those devices. So switching back, so here you can see that in the equipments in the Munich, the errors that are being happened. So somewhere that in the test line item, the energy consumption goes below, in the alert sections the energy consumptions below the minimum one. Somewhere for some of the devices, which is being the number of production units is below the minimum one. So what I could do, if I choose any particular alerts over here, or I can choose any values from here, so it would be loading the data from the Azure time series insights, and I could be able to analyze those alerts that's being generated due to a report value, or from a calculated operational equipment efficiencies or the KPIs factors, which is exceeding the competing threshold value. So this panel will show me the alerts at each level of hierarchy, from the station level view to the global view. And these alerts will also contain the description of the alert, like date, time, location, the number of occurrences. So such kind of details we could be able to get. So it would be loading the data in backend from time series, and then from the time series we could be able to get such alert details with date, time, location, number of occurrences. And furthermore, on top of that, we can gain the insights to the data that is causing the alert using the time series insights data. Time series insights data, it is being available to visualize in the alerts when applicable, and we can even just close the alert, or we can acknowledge the alert. Optionally, we can also take the complex decisions, like in order to check for the overall operational efficiencies over the period of time, or if we want to check the if we want to call an OPC UA method. I'll be showing next how to call the OPC UA servers over there. We can check the overall availability sectors, we can check the performance levels, we can check even the quality status over here. So such kind of matrices we could be able to check. Next, we have the options like to connect to a OPC UA server from connected factory. So let me just connect with an OPC UA server from connected in Munich assembly line. So here I have just connected to the assembly line here. Now from the server, I would like to first call from the server instances. So from the server instance, I would like to call the OPC UA server. Refresh the page once again. Okay, please know to all of our attendees that we will be sharing the recording of the session to all of our attendees today. And in case anyone couldn't be able to share your official mail ID, so I would request to please share your official mail ID so that we could be able to share the resources for this webinar, like the presentation deck and the recording, because we could be able to share only through your official IDs, not any other personal ID. So feel free to share your official mail ID so that we could be able to share the resources of this webinar. All right, so here we could be able to publish an station telemetry. So for example, here you can see that I have been connected to the server, and from the servers in the OPC UA server, I would like to publish the particular OPC UA node. So what I did, I just clicked on the cycle time in the station telemetry, and I have just made a call. So this method call having succeeded once I made a communication. Similarly, I can also do a command and control. So in the station commands, for example, let me dig into the station commands, and under the station commands, once I click on open pressure release value, for example, there I have been just doing the right click. One second. Okay. So let me just connect to the OPC UA server once again. So I'm jumping to the station commands. So under the station commands, once I'm selecting the open pressure release valve, so once I right click that, I could be able to call the particular command and the methods. So the connected factory, it allows us to command and control your industrial devices directly from the cloud itself. So we can use this feature to respond to the alerts generated by the devices. For example, you could also send a command to the devices from the cloud, and also you can find the available commands in the station commands node. So here, this particular nodes that I have just demonstrated. So in this particular nodes, you can find the various types of options that the station command nodes in the OPC UA server's browser tree. Now, in this particular scenario, we are opening a pressure release valve in the assembly values and in the assembly station in the production line item in Munich, and we can also use further the command and control functionality that's to use in any of the station node, like not only just from Munich, maybe in Johannesburg or in Seattle production line item, whenever we would be able to see there is an alert or any issues having happened with the OPC UA server. So, and also we have the features even to connect with our own gateway. So if you are considering to use your own IoT gateway that's to be using with this kind of scenario, this kind of features, and you would be able to add your Windows-based or your Linux-based IoT gateway servers, and you could be able to connect end-to-end through the Docker system. So similarly, not only just from Munich, we have the series of items being available from the various production line items, just from Seattle, from Mumbai, from any of those locations. So you can see in Mumbai there is an errors happen through the packaging and assembly line sections, and if you want to generate an alert, for example, there is an options to close an alert to execute an action. So such kind of flexibility we have, because since here this particular production line item is not needed because everything working fine here, the number of manufacturing or the number of discarding the faulty time, actual cycle time, since everything is working fine over here. Now, with this particular feature, if I would like to show you how the time series insights, the time series environments looks like. So let me open the time series insights from this connected factory solution. So here goes my time series insights, and I'm just jumping to the time series environment here. So what is about the time series? So typically Azure time series, it refers as a series of connected events that's to be coming out in the real-time data processing, event processing scenario. So just to tell you that Azure time series environments, it is right now in preview mode. and it has just released last month in the midweek of April. So it is all about just like how with the increasing connected devices and massive advances of collections of data, because today business is struggling a lot, that's to quickly derive the insights from the sheer volume of data that is generated from the geographically dispersed devices and the solutions. So in order to build the near real-time insights in second with IoT at scale, Azure Time Series Insights enables us to ingest the hundreds, even millions and billions of events from sensors events per day. And it makes the new data available to query and to gain the insights within 1 minute. It also enables us to retain the data for months. Time series insights just to help to optimize, just to enables you to query over the combinations of near real time and historical even terabytes of data in seconds. So it doesn't work on the pre-aggregated one. But what it does is actually that it stores the raw events, and based on the raw events analysis, it could be able to deliver the processing of the real-time events. So you can define over the events, over the periods of time, how the series that could be able to process the events over the period of time, and that could be like over a massive scale. So additionally, it is also enables us to upload the reference data to Argument to enrich the incoming sensor data. It is also helps to define a heat map, a strong heat map, just to provide the event source, and over the period of time, that's how to compare the data across the various sensors of the different kinds, event sources, regions, IoT installations. So such kind of information that it's able to provide. Azure Time Series Insights, it has some of the standardized methods as well to just being accessing device telemetry in real time. And it's also being capable to produce the event sources, or just to be the content in absolute real time. So without any development effort, it produces the help that time to detect and diagnose the problem that has dropped from the days to minute. With just a few clicks, we can visualize end-to-end device data flow. So it's helping us to identify and address the customer and market needs. Right. So, and also overall, it's easy to get started. So in this current time series insight environment, I'm just showing you for this particular connected factory solution, what are the overall value-wise, the series details, the event-wise analysis. It is just a real-time events that has been passing through over the couple of days, last couple of days that it has been processing through, and even the application URI-wise, the demonstration. So similarly, if I show you the heat map over, so you could be able to see that over the period of time, what was the average events that has been passed to especially in the OPC US SCADA portal. So what are the maximum events, what are the minimum average events that has been passed to. So it has a very strong understanding about in terms of starting with Event Hub, IoT Hub, and when customers can get started with time series insight just in a few minutes. Just enter your IoT Hub, Event Hub configuration from the Azure portal. Time series insight will connect and start pulling and storing the real-time data from within just a minute. So the service enables us to explore, compare, and correlate the varieties of sensors seamlessly. And it also provides a very intuitive user's experiences that enables to view, explore, and drill down the various granularities of data, like down from the events. It provides a SQL like filters, aggregates, ability to construct, visualize, compare, and overall the various time series patterns also, like power of REST queries and all. So in Azure IoT Suite Connected Factory, we could be able to see such kind of time series insights, and it's actually the time series that I'm showing you right now. It's based on the time series query infrastructure itself. So that was all about end-to-end about time series and Azure Connected Factory analysis. Quickly switching back to the presentation. So I've just switched back to the presentation and hope you're able to see the deck right now. So before jumping into the case study demonstrations and all, so I would like to talk about a quick review regarding the Azure technologies behind the scenes. So it's all about the technologies and the demonstration that you are seeing today. It's all about based on the Cortana Intelligence Suite, so which is being able to transform the data into the intelligible actions. So Cortana Intelligence, it's all about like from information management to the big data store to machine learning analytics and further to derive the intelligence. So it is all about like how you can define the actionable insights from your data. So even with Azure IoT Suite or Microsoft IoT Suite, it's all about like from the devices end to end, how you can gain the subsequent knowledge about those real-time event process through Stream Analytics, through Event Hub, through the blob storage, and you can build an interactive web or mobile-based application. And you can analyze the real-time sensors or the data movement through the real-time processing through Signal R. It could be built on Azure Web App, or it could be built with ASP.NET with Signal R functionalities and all of that. Of course, web jobs is one of the part that we can apply for the implementation side. So as I was talking about Azure Event Hub or IoT Hub, so Azure Event Hub or IoT Hub, it's all about like it's a managed services. So no hardware, software is needed at all. So it is very ease for provisioning since it's a managed service. It's based in cloud. So it has also a very low cost devices, services that without being directly installations of any of the particular software, just in few clicks you can connect your on-prem devices or your hardwares or sensors that's to be connected through these devices, and you can apply the end-to-end connectivity, and those which that it being able to just ingest the millions of events per second. It has features for scalability on demand. It is a guaranteed delivery. It has an end-to-end connectivity model as well. Azure Stream Analytics. So Azure Stream Analytics, of course, it's a vast amount of data when it has been flowing through the high velocity over the wire today. So organization, they need to process and act on the series of data in real time, which can dramatically improve the efficiencies, and it can differentiate themselves in the market. So scenarios, such case of real-time analytics solutions, it could be found across all the industries. So personalized way that real-time stock trading analysis or alerts, which is being offered by the financial services, in the various types of IoT services with clickstream analytics or in dynamics CRM systems. So it's all about the applications issuing alerts. So when customer experiences within the time frame has been degraded. So in those of the scenarios, we need a reliable, cost-effective managed solutions. So in Azure Stream Analytics just helps us to leverage a managed, cost-effective real-time processing engine. So just to have an insights from deep insights from the data. So, of course, Stream Analytics capabilities I have already demonstrated during the demo time, that how we can configure the inputs, outputs, and we can define a series of layers through the T-SQL-like manner. So, output also from the complex event processing layers that could be also come to a persistent storage, like from dashboards and back to the devices. Coming to the machine learning, so Azure Machine Learning, we have the flexibility that it's a technique of data science which helps the computers or to make some intelligence on top of data in order to forecast the future behaviors or the outcomes or the predictions. So these types of forecast or predictions from machine learning to make it can make the apps more intelligent, even more smarter and scalable. So machine learning helps to recommend the other products, even just like based on the previous purchasing model, like the recommendation, the prediction model. When you swipe your credit card, so machine learning compares the transaction to the database of the transaction that helps to detect the fraud analysis. Similarly, when your robot vacuum cleaner vacuums the room, so machine learning helps you to decide that whether the job has been already done or not. So there are all over that. It's all about applying the machine learning on top of cloud predictive analytics. So Azure Machine Learning makes it possible to quickly create and deploy the predictive analytics model as an analytics solution in the cloud. And we can get the Azure Machine Learning as a part of Cortana Intelligence Suite. We can gain the predictive analytics uses, the usage based on mathematical formulas like algorithms, which can analyze the historical current data to identify the patterns and practices and to design the trends in order to forecast the future event. So in the Machine Learning Studio, if you start writing the application to build the intelligible learning models today, so you could be able to see that there are various tools that are available to complete the machine learning solutions in the cloud. So you can create the predictive models. You can start from Cortana Intelligence Gallery, and from there you can utilize predictive analytics situations. You can define an analytics model everywhere, like whether from telemetry data analysis, whether from predictive maintenance to customer churn analysis, or the fraud detection scenario, or in case of weather forecasting model. So Azure Machine Learning is today, it has been mainly based onto the 4 different main pillars of the data science algorithms, like classifications, whether we need to classify a trend or the fact regarding the data pattern. We need to define a regression, that whether the particular customer has been churned or not, whether the particular incident has happened or not, to identify a pattern from the predictive scenarios, or even based on the classification regressions, we can define some case of supervised recommendations, like what could be the next possible products that customer would like to purchase next. So shopping enjoy in terms of retail scenarios, recommendation is one of the major pipeline to go up with that. And also we have in machine learning the scenarios like clustering, which is a part of AI, that in the deep learning and the neural network scenario, we identify the clusters, and also we need to define the anomaly detections, like which is being already happened, or what are the next possible outcomes that can happen from those of the data exploration. So of course, in the machine learning concepts, we have the features like data exploration, descriptive analytics, predictive analytics, and from predictive analytics, we move further into prescriptive analytics. So predictive analytics, as I said, it's the process for building the models from historical or the eventual current data in order to forecast the future outcomes. We have two different types of learning here in Azure ML, like supervised learning and unsupervised learning. Supervised learning algorithms are the trained with labeled data, so where data comprised of the examples like a model that identifies a fraudulent credit card transactions, or it could be trained from the data set that labeled as the data points or the fraudulent charges. It could be based on unsupervised learning, that where the data has no labels, there is a goal that to find the relationship for the data, but you might want to find out the groupings of customer demographics which are going to buy the similar categories of product. So in machine learning, we have like the options like how to get the ML learning, how to get the algorithms to be available. So in cloud, normally on top of the various algorithms when you apply, like through HD Insight, through SQL Server VMs, through blobs and tables, or even from local, we can upload the data like through the CSV files, through the Excel or desktop files. And on top of that, we can build the models on the ML Studio through ML API services. And finally, we can release those API as a web part, or just we can publish them as a web service. So we have the training data options where we can train the model from the data. We can use the known data set. We can make some adjustment to the models passed on the data characteristics to get the most accurate answer. In Azure ML, it could be built from algorithm modules that's to be used to process the training data, and it can use a functional modules such as to build the scoring modules. In supervised learning, always we have been used for training a fraud detection model or some kind of transaction model. That's either it could be like fraudulent or valid, and we can split the data set randomly. We can use the part of the trained data model or the part of the test or the evaluate the model. So there are different types of machine learning algorithms having there, like in terms of anomaly detections, like flagging the unusual events, or categorical data, classification data, model for organizing the data into the categories. We have numerical data. The data has meaning as a measurement, like to discrete the data or referred as a quantitative data. We have like prediction data. The prediction, as I said, it's a forecasting, the prediction maintenance warning. So when the equipment will be going to fail, when the production line item can be failed, and what are the possible outcomes that need to be taken care of. So an evolutions of the model just to define the prediction analysis is a score. Similarly, regression, it's a model for predicting that a value based on the independent variables, such as predicting the price of the car based on the year and the manufacturer. Similarly, score, like a predictive value generated from a trained classification. So classifications also just return a score for probability of the predicted value. So with terms of that, I'm just jumping into the next demo that was based on the predictive maintenance. That's an end-to-end architecture. So today, such kind of architecture is being well enough to see, like from event producer to event ingesters to transformations to enrich data with Azure ML, and finally for the long-term storage and the further into presentations and actions. So with that, I'm going to show you, before jumping in further, what about the how the predictive analytics happens. So let me quickly share my desktop. And first, let me get started with my predictive analytics, stream analytics jobs that is related to a weather predictive analytics model. So in the weather predictive analytics model, it's a weather forecasting which is being using the sensor data coming from IoT Hub to Azure Machine Learning. So you can see that I have already built the weather telemetry here. the stream analytics jobs. So the stream analytics job is being collecting data actually from IoT Hub, and IoT Hub has been again connected to the device identity, that it has devices that is sending the data from one devices to the another devices. So I have a simulator application is already there that is called as device identity. So I have some level of device identity applications that is being responsible for sending the data to the IoT Hub, and also I have a simulated device application in Visual Studio Simulator. So what you can see here is basically is a receiving apps that is being responsible for receiving the nature of applications. So I mean receiving the events, actually the temperature alerts and such kind of details. So what I'm doing, I'm just starting the virtualized streaming one. And instead of virtual data simulator, you can also use even the real-time data simulator as well. So if you have already a Raspberry Pi and that has been connected with your real-time sensors like temperature sensor, heat sensor, so you can connect both of them, and you can make a communication directly through Event Hub here or IoT Hub. Here I have, since I can't show you directly as a remote webinar, directly the devices, how it has been connected to IoT Hub, I have used the virtualized data simulator. So you can see that how the data has been sending and received by the various levels of partition. So from the devices, the data has been sent, and in the IoT Hub, the devices, the device information has been received with the device ID, the temperature details, the humidity details, and all such kind of things. And here in the streaming analytics, I have defined through the query also I have defined the function. So actually I have used a weather prediction model function. So this weather prediction model I have collected from Cortana Intelligence Suite. So here is my machine learning model that I have added here. So to add the machine learning functions, what I did, I have defined the function signature, the temperature, humidity, and also I have provided the workspace, I mean my ML workspace URL, and also I provided the workspace key. And once it has been done, I have also defined a query according that is suitable with collecting the data from IoT Hub, and from IoT Hub, once the data has been coming from IoT Hub, it has been processed through the complex event processing, and on top of that, it has been applying the intelligence through the machine learning layer. That's being probabilities of rain, that is actually I want to find out from the analytics, and further it has been put into the Azure Blob Storage. So here in my Azure Blob Storage, the output has been stored as a CSV file. So if you would like to see the output from the Azure Blob Storage, so we could be able to see. So let me download it, and we could be able to show you on that. So I'm just quickly downloading it, the output data sync, and so this is the data, output data that this looks like. So here you can see the final possible outcomes that's been coming out from the complex event processing stream analytics IoT pipeline, that the time, temperature, humidities, and it's also being referring from the ML workspaces that it's being identified that what are the possibilities of rain. So in this particular current time, in this particular latitude and longitude, in the humidity level, what are the different levels of possibilities of rain? So 0.048899, that is actually defining that there is a slight possibilities of rain that it could be. And I have also defined the corresponding in the ML workspace, the prediction model that's being available. So this is how we built an end-to-end pipeline with Azure Machine Learning with Stream Analytics weather prediction analytics model. All right. So jumping back to the next section of this presentation, which is a very new interactive module. That's how we can integrate Service Fabric, Azure microservices with IoT solution. So before that, let's to have a quick overview that how we can integrate Azure Service Fabric with IoT Hub. So Service Fabric, as we all know, it's a multi-tenant applications that it is basically it's an architecture based on Azure microservices, where actually all the app services that we are known to us that for whenever we have been deploying an application like any app service application, so it has been deployed on top of the VM. So in microservices in Service Fabric, the design patterns is like that. The application instances is going to be deployed on top of a fabric, like on the different user models. So in this Service Hub and IoT design patterns, like whenever we can integrate Service Fabric with IoT and end-to-end demonstrations. So the sample project that I'm going to show you now, it's all about like how we could be able to build a multi-tenant IoT solution using Azure IoT Hub for device message ingress, like how to ingress the message from IoT Hub for device messaging, and also how to use Azure Service Bus for device message access and for processing purposes. So as I was talking about like IoT Hub and Event Hub partitioning status, so a partitioning from IoT Hub to Event Hub, it's an ordered sequence of events. It consists of multiple partitioning module. So and also whenever you are being connecting as an ingester like IoT Hub or Event Hub, it's actually the number of partitions, the number of consumption unit that where the data could be stored into as a part of partition model. Now, in the partitioning concept, of course, for example, in Event Hub, there is an offset is being there, which is a position in the event stream of partition. So consumers must keep track of this offset outside of Event Hub or IoT Hub. And this offset is actually just being keeping track of the offset values. So likewise, in IoT Hub and Event Hub partitioning, we have multiple independent partitions there, which can contain the own sequence of event data. Partition has to be distributed across the machines for scale, and consumers also can coordinate with each other to read from like the multiple partitions. Likewise from Event Hub. So such like that, we have a concept in Event Hub that's called Event Processor Host, which is being responsible for consuming the events from stateless workers. So from IoT Hub to worker role to again from the multiple worker roles, we can define the end-to-end partitions like that using the event host processors. Now, how we can build the multi-tenant IoT application with Service Fabric. So in this architecture, the solution architecture that you can see, that it's basically designed like how from the different devices coming out from the various companies, the devices which has been installed in multiple geographical location, the data from those devices has been processed and it has been ingressed into IoT Hub, and from the IoT Hub partitioning and processing, it has been ingested into the different applications, and from the applications it has been pushed into the company's tenant model. So, and that's all having managed end-to-end through a Service Fabric. So in this demo, what I'm going to do, I am going to show you basically how through Service Fabric we could be able to deploy the IoT solutions. So for that, I'm just quickly jumping into my desktop. If you face any difficulties for viewing my desktop, so feel free to write in the IM window. All right. So what I'm doing, so here I have already the solution. Let me open the solution first. So already I have the solution that's being ready with me. That's the servicefabric.net IoT. So this is the servicefabric.net IoT. I mean, the solution is available in GitHub as well, which I'll be sharing with you, the resource. So basically, what are the prerequisites for building the solution? We need, of course, Visual Studio. That I have a Visual Studio IoT solution for specifically for Service Fabric. I need to have a Service Fabric dev environment, which I have in this my dev machine, and also I need to have IoT Hub, which I already created in Azure Portal. IoT Hub, again, just like same way during demonstration I have shown to you, you can create from in the Azure Portal directly from create new, and from the Internet of Things you can create from choosing an IoT Hub. Now, for the deployment, what we have to do, we have a PowerShell script here that I use to deploy. So under build, I have basically this PowerShell script which is being responsible for building up the solution. So this is the script actually that needs to be built, and it needs to connect to the Service Fabric first of all. So this is the PowerShell script that needs to be connected first to the Service Fabric cluster, and then it can call the various configuration parameter from Service Fabric cluster itself. In terms of architecture perspective, I have just demonstrated about a conceptual architecture, but this is the overall end-to-end solution architecture that you can see that from the field devices, that through the gateways and the device simulator console app, while the data has been moved into through the batch data through the various partitions in the IoT Hub. Now from the various partitions of IoT Hub, the device batch data has been moved to the ingestion applications, to the stateful routing services, and from routing through the stateless web services, it is further moved into the stateless data services like in the various tenants of Service Fabric. And further, for the cold storage of the data just coming out from Service Fabric cluster, we have pushed into Azure Blob Storage. So that is almost about the application end to end so far. So what I did after deployment of the PowerShell script, I have connected to the Service Fabric cluster, And since I have basically in this dev machines, I have 5 node clusters being already connected. Now here also I have Service Fabric solution, which basically pointing me to the Service Fabric portal. So here you can see this is the Web API portal. That's the local host it's being running through, and from the portal I can basically can add into the Service Fabric ingestion applications. I have already added some IoT Hub integrations, like I have added the IoT Hub connection strings, and also I have defined a tenant applications. So if I click on the application for IoT Hub, which is running from Service Fabric cluster, so Contoso IoT Hub is basically my IoT application which is being running from the Service Fabric multi-tenant instances. So this is, you can see that only one device is it's already being connected over here. Now next what I would like to do here is since I have already been connected so far, so let me just run this app once more. So once I click on start, the application should be able to run. And here also I can throw some messages. I can basically added some device instances and so forth. So what I'll do, let me first add a connection string for IoT Hub. So I have couple of IoT Hub is already been provisioned. So let me choose one of them. And so you can collect a connection string of an IoT Hub directly from shared access policies. And from there you can select IoT Hub owner, and from there if you select under IoT Hub owner you can click on connection string and just copy it and paste it here. Once you did that, it would ask you to the Service Fabric cluster address. If your Service Fabric cluster is being deployed in Azure, you can provide the cluster address. If you are working it local, so you can keep it blank, just press enter. So then you could be able to see the various sorts of commands to register a device or to register the random devices. I have already registered some few of the couple of devices, like my first device, device ID 1, device 1, such kind of devices. What I'm interested, I'm interested to send some data from a device. So I'm just selecting a tenant first. So since I have already created a tenant called Contoso IoT Hub, now I'm going to add a device, that device 1. And you can see that some data has been sent. Now I'm interested to send data from all devices. So just first defining the tenant, that's my Service Fabric tenant, and number of iterations I'm defining at 6 iterations. So 6 times from all of the devices, the data, the weather temperature data that has been sent to you from the Service Fabric tenant applications. And the data has been sent actually from IoT hubs devices, from the IoT devices to the Service Fabric tenant application. So this is the way that how we could be able to build, that's the tenants of the systems to consume the messages from device field gateways through the number of IoT Hub instances. Tenants can view their devices, device messages through the web UI. Messages could be sent and expected to the tenant name. And it's the pattern that how the messages has been read from IoT Hub, which is through the event hub receiver. So it's which is a partition stateful Service Fabric instance. It's a multi-tenancy using dynamically created name instance services. Service-to-service communication is being applicable here, which is using HTTP, ASP.NET Core, and services exposes the HTTP endpoints. And overall, for the demos, we have used IoT Hub, Service Fabric to host the message processing application. We have used Azure Storage overall. So this is how today we can work end-to-end, like Service Fabric with IoT solutions. And before finishing today's demo, I would like to jump into a customer success story, so which is pretty much useful for this context, just to have an end-to-end understanding, like what are the possibilities today with Azure Internet of Things, and what Microsoft can provide in terms of your predictive analytics business solutions. So one of our customer, that's Rolls-Royce, that have implemented a monitoring portal to track the way that how their engines could be used and how it could be allowing them to build the smarter, safer, and more reliable engines, and how it could be also improve their customer relationships with airlines. So it could be able to offer the further intelligence into the way that how the planes are flown. So the ultimate goals for Rolls-Royce here, that's to streamline the servicing and to reduce the fuel burn, because most of the time the major issues in airline industry is that the planes needs to wait because of the fuel inefficiencies. They needs to identify that what would be the possible levels of the fuels that needs to be filled up in the tank, and how it could be lowering down the operational cost in terms of airlines and reducing the risk for unplanned or unscheduled maintenance and the passenger delays. Because just in the efficiencies, increment of efficiencies, just even few percentage, it can reduce up to the even thousands or millions of dollars per year for airline industries. And that is the ultimate goal with IoT today. So the system that I'm going to show you now, it's built using Azure IoT Suite, Cortana Intelligence, Power BI, and utilizing, of course, machine learning. So without further delay, I am going to log in into the application. So I'm going to log in as a supervisor in this application, and you can see basically the predictive analytics dashboard for Rolls-Royce that is built with Microsoft IoT Suite. So in this business where basically the unplanned delays or unscheduled maintenance can result over 1 million per day in trickle-down cost for airline. So just not to mention about the delays, how it affects the passengers, and the scheduling is very critical. So in this demonstrations, you can see that at a glance, that's a consolidated view for an airline fleet, like including the current location, upcoming flight schedule, planned maintenance, and the maintenance capabilities at the ground location. So we can be able to see that some of the operational matrices, starting from operating KPIs to scheduling stress, on-time performances to fleet status, flight scheduling. So such kind of details. That's all of which is leading to the indicators that of a potential disruptions to the fleet operations. So the information which is populated by live and historical data, it's being ingested through Azure IoT Suite. As an aircraft that landed and connected at a gate. So data from most of the recent flight, it needs to be updated, and it needs to be processed and analyzed by Cortana Intelligence. So as you can see in the beginning, like a flight that flying from here. So let me just select, it's actually the flight that is flying to Frankfurt. That has an escalation that it requires investigation to ensure that it can meet its planned flight schedule without disruption. Now, if I drill down further that what happened to this particular flight just flying from Frankfurt, so we can see in the early watch list of the fleet status that there is some primary fuel pump issues that have been happened over the period of time. And also we could be able to see that the possible schedule stress over the period of time, like which has been forecasted and compared to the actual values. Now here, if I click on the flight, to understand about the aircraft overview. So aircrafts and the engines, that's are very complicated machines, and it needs to be well monitored. So the aircraft dashboard is actually present here. That's the operational and contextual information for this particular aircraft. Now here you can see that it's actually being able to produce here the successful critical system details and their health status, as well as RUL, the remaining useful life status calculation, which is a result of predictive analytics coming through machine learning with the IoT Suite. So we can see that the plane is at the gate at the Frankfurt, and not due to the takeoff nearly for 4 hours. And we can also see the results is the aircraft is not due to the maintenance for quite a long time. So fuel efficiency is a critical, and that's why you can see that there is a line graph that represents the altitude versus the hours timing, the analytics over here. Because for few airlines, like when the plane needs to be landed to a high altitude airports, like in US, for example, like Colorado Airport. So such times we need to understand, for an aircraft engineer, they need to understand that regarding the altitude, regarding the pressure level, regarding the fuel efficiencies level, or regarding the equipment level, the nature of more efficiencies and the accurate level. So here goes the engine details, like the remaining useful lives for the 2 different engines for the aircraft, and also the aircraft fuel levels from the left wing to tail to the center tank and further to the right wing tank. And also, as a aircraft overview engineers, they could be able to get even the details about, from a captain perspective, what are the remaining useful life for the engines, what are the fuel levels for the various tanks, and how much it needs to be filled further in order to avoid the unnecessary downtime and unpredictable scheduled failure or unscheduled failure. So with that, if we need to identify some level of understanding. For example, for this particular aircraft, there is a propulsion system error. So pilot discretions, if she wants to have a more detailed overview of the engine details. So she should be able to find that through this visualization, we can see that even the aircraft has been flying over the short-haul routes, but there are particularly some hard-on engines that for which it is not able to run at the constant or cruising RPM or much at the more flight that is being subjected to frequently to the stresses and ascending and descending. So in the scheduling chart that is being visualizing for here, like normalized fuel burn or the engine systems that's being referring to, like primary fuel pump and all. So it is actually being showing that couple of which that looks that a relatively harsh operating environment, and we can see that why this is the part is being reaching to the end of the service life. From the servicing perspective itself, you can see the visualizations like in the fuel pump speed for the airline, or the power pump, which has been the expected layer and which has been the actual layer, or the valve position over the period of time, the fuel flow over the period of time, and the temperature differentials like over the period of time, and the unit health for the period of time. So such kind of details, that also means that there will be a less to do that in the next scheduled maintenance window, just being shortening the downtime of the aircraft. So any point of time, if the pilot thinks that there needs to have a maintenance that needs to be recorded, so she can select the request maintenance tab, and from which she can have an overview for the primary fuel pump versus the predictive RUL. And so that she can notify the airline staff, the aircraft engineer, to assign the spare parts, and to the maintenance team, and finally that they can update the various aircraft records. So these actions has been proposed in the dynamic CRM records and the field services, just being notifying to update the aircraft records, and to have the specialist to be in the ground engineers, so especially just assigning the spare parts, ordering more if necessary. And finally also she can confirm that whichever the particular fuel pumps that need to be listed, that needs to be replaced also for the next few hours, and how the aircraft would be able to do the further success way that for the next destinations and on time. So just in this way, I just like to demonstrate that how Microsoft and Rolls-Royce have been working together and using the intelligent cloud to accelerate the Rolls-Royce views transformations, and utilizing the power of machine learning, Azure IoT Suite, Power BI, so those kind of features, that it could be able to understand the remaining useful life. And it, of course, it is accelerating the Rolls-Royce digital transformation with IoT, so improving their products through taking the customer service to the new height. So with that, I would like to have to understand if there is any question or any concerns regarding the technical content for today's webinar, because we have reached almost towards the end of this webinar. So I would like to understand if there is any questions, any queries that you might have. So feel free to write in the IM window, or if you'd like to discuss also with me, so we can unmute yourself. So feel free to write in the IM window any questions, any queries that you might have, or if you have not shared also your official mail IDs, so feel free to share. I mean, without your official IDs, we could not be able to share the resources of the webinar. So I would like to thank you to everyone for your time and the patience